So you probably read the book Crossing the Chasm by Geoffrey Moore. And that book talks about how it provides a methodology of how technology is adopted by a marketplace. And it talks about the chasm being a period of time when we go from early adopters to the early majority. It's a painful period of time. But the quantum chasm is different. It's the big elephant in the room, and that is, we still do not know how the first applications will be commercialized for quantum computers. So today, I'm going to talk a little bit more about when it will happen, what applications will likely be commercialized, how to do it, and most importantly, who will be crossing that chasm first. So let's talk about when, because that's probably the big question. When is it going to happen? And I want to give a little bit of context about where Google is at to give you a feeling of when things are going to actually happen. So this is Google's chip. You can actually, this chip is actually kind of the size of my nail, and it lives within this thing called the dilution refrigerator that Bo had talked about. And this one's actually even bigger than the D-Wave. This is probably, it's bigger than me. Like, it's the very, very large refrigerator. So this chip will not be going into your cell phones anytime soon. But not only have we built the hardware, what we've also done is that we've ran some applications. These are applications that you know from your textbook, your high school textbook. Specifically, we went to simulate hydrogen, H2, and we looked at what they call the dislocation energy. And via a combination of really smart hybrid classical algorithms, last year, for the first time, we were able to predict the dislocation energy of hydrogen. And this is actually a huge achievement because it gives Google, at least, the confidence that from going to simulate hydrogen, we could simulate larger molecules, we could simulate catalysts, we could simulate the Haber-Bosch process. And we feel that by this kind of use case, we are confident that we can do those kinds of applications. So what's the quantum timeline? By the end of this year, we hope to hit a milestone called quantum supremacy, which is for a very specific algorithm and application. This is more of an algorithm. It doesn't have any practical real-world uses. We will, for the first time, prove that quantum computers are orders of magnitude faster than the fastest supercomputer. However, here's the catch. These early computers are not very stable. In fact, for these superconducting qubit computers, they do something they call decohere. That means that the bits would flip from 1 to 0. They would have errors very quickly, on the order of 100 microseconds. And so it's actually going to take around at least 10 years to the point that we have very, very stable quantum computers. But even within this period of time, the next 5 to 10 years, we think that there's going to be some transformative applications in the area of chemistry, optimization, and AI. And I want to give you some context on history. In fact, if you look at the first universal digital computers, it was invented in 1941. In fact, it was invented in Germany by Konrad Zuse. But however, due to the war, World War II, he didn't get the investment he needed to actually push forward the computer revolution. It wasn't until 1955, 14 years, that stable silicon-based digital computers were created. But even within those 14 years, there were a few extremely transformative applications, specifically in the area of nuclear physics, which helped the US develop both nuclear weapons and thermonuclear weapons faster, as well as a space race. These things may have not happened had computers not existed. So I talked a little bit about the timeline. It's going to be 14 years, very few applications, but extremely transformative. The question is what? So we talked a little bit about technology, right? But I think the industry, but in order to figure out what actual applications, you have to figure out which industries will actually develop and leverage this technology. And my theory is that the industries most likely to develop quantum applications are industries that are undergoing disruption today. And I'll give you some history lessons here. So you think about in the 1940s, the industry under disruption was the warfare industry. It was going from conventional warfare to nuclear warfare. And because of that, governments would spend lots of money on unproven, unstable technology just to get a competitive advantage. And the reason why is because it's an existential threat. If they don't do it, they literally might die. So today, what are the industries that are having existential threats? Pretty much all of them. And the big disruption, it's technology. But there's no industry that is going under existential threat more than the automotive industry. The automotive industry has threats from two directions. One is electrification and electrification of cars, and the other is self-driving cars. If car companies do not actually get leadership in any of these areas, they could potentially see themselves going out of business, which is great for quantum computing because the first applications is around chemistry, which you need for building better batteries, and optimization, which is needed for building self-driving cars. And we believe that these are the kinds of partners we want to work with at Google because we know that there is the organizational imperative to actually make a change and invest in the long term. Now for the hard part. How are we going to do it? So when you're building a computer, when you're building a regular application, the first thing you ask is, what kind of computer are you building it for? And today, when you're building an application, you think about CPU, memory, and bandwidth. Those are the three parameters that most people use. But what are the three parameters for quantum computers? It's actually not very obvious, and I'll try to explain a little bit what it is today. The first one, which everybody kind of intuitively understands, is the number of qubits. So the number of qubits is the number of it's kind of like bits, right, as we heard before. But the two other parameters that's not well understood, and I'm going to first talk about this, is the gate fidelity and the gate depth. So because these computers are very unstable, whenever you do an operation between two pieces of memory, it introduces a little bit of error. How much error can your application take? It actually depends on the application. It also depends on the algorithm that you use. So we've heard a lot of talk about building algorithms. The reason why it's so important and it's so hard is because you need to build algorithms that can sustain, that can deal with the fact that the fidelities are not perfect. The next parameter is this thing called gate depth. Because as you heard before, these things are unstable. So you need to make sure that the application completes before the bits start flipping. The second problem on how should an enterprise be ready for quantum computing? Now, the truth is, depending on your industry, when a practical quantum computer is going to be available is an unknown. So how do you plan for the unknown? Well, you could obviously be reactive. You can say, okay, when a quantum computer is available and I see my competitors building an application around it, I will do it at the same time. The fallacy of this approach is, unlike, let's say, mobile technologies or web applications, it's going to take a long time for you to do the research, development, and productization of these applications. My opinion is going to take at least 7 years. So, the better approach is invest into research now. More specifically, open research. And the reason why we say research, open research, is by doing research in open, you can get more people to give comments on whether your application is truly improving your system. The other issue that we see a lot of enterprises run into problems is that if they do it in a closed way, they don't know if the application they built has truly a quantum speed up or not. And because of that, there's a lot of false signals. And we always hear in the news, some company claims they have some speed up, but there isn't very good evidence around that. So this research actually is a much more cost-effective mechanism for doing development. And you want to line up, by doing research, you know then when the practical quantum computer exists, so you can align your development to end at the same time that the practical quantum computer comes out. The next thing around how is that this is actually a very risky field. There are still a lot of hard science and engineering problems. So even if you had a quantum computer that can run an application today, there are a lot of scientific and engineering milestones that still needs to be crossed. And so instead, we suggest that you do an incremental approach. Google is actually creating what we call the Quantum Supremacy Roadmap, which is experiments on well-understood problems where you demonstrate quantum computers are much faster than classical computers. And for companies that take this approach and solve these particular problems, they are most likely to be able to bring it back in-house and turn into applications. So let me give you an example. I'm going to talk about the chemistry roadmap. So the first item in the roadmap is a very textbook problem. It's called the electronic gas problem. This is almost all chemists understand this. Maybe the second milestone after that would be simulating a textbook catalyst, namely the chromium dimer catalyst. And then you would actually simulate real processes, like the Haber-Bosch process. And by having these really well understood milestones, it makes it much easier and more predictable to get progress and build actual applications. Regarding the Haber-Bosch process, the reason why we care about that so much is because, number one, everybody understands it. And number two, it's a $72 billion industry, and it's only 15% efficient. We know plants are 70% efficient. So if you can simulate the Haber-Bosch processes today, whoever is able to do that is most likely the ones who are going to be able to figure out how to make them more like plants, how to increase the efficiency. All right, the biggest question is who? And I want to go back to history again to give us some inspiration. This woman, her name is Grace Hopper. She is arguably the first commercial developer, and I want to give a little bit of her commercial digital application developer. She was a math professor during the outbreak of the war, World War II, and she decided to enroll in the Navy. And when she tried to get into the Navy, she was immediately rejected because she was 36 years old, too old, and it turns out that she was too young too. She was too light. So instead, she started working on the Harvard Mark I on the Manhattan Project, doing critical calculations for the Manhattan Project. Building applications then was really hard. There was no compiler. In fact, she is the inventor of the compiler. There was no programming languages. In fact, she invented programming languages. She invented COBOL. So, and today, she's not only known as a pioneer in computer science, but she's also thought as a heroine for women in computer science. How does she succeed? Well, three main things. Number one, she had a very clear mission. She was working on a problem that she knew was an existential threat for the United States at that time. Number two, she surrounded herself with the best domain experts. The best nuclear physicists in the world were all working with her hand in hand. And the third thing that she had was access to the best hardware engineers and best hardware for building the first computers. She literally debugged the first computers with her engineers by reaching into the back of the computer and removing live bugs from the electrical mechanical switches of those computers itself. So, what can you do? You are all leaders of transformation within your organization. How can you create the same environment that Grace Hopper had? Number one, figure out what are the existential threats within your organization. Make those and figure out how you can make the quantum developer work on those threads. Number 2, get your best domain experts. I don't care what industry it is, whether it's chemistry or self-driving cars, get the best domain experts and surround the quantum developer with them. And number 3, get them access to the best hardware, but also give them access to the team that's building the computer itself. And I think, and so last, I just want to leave you with this thought. The quantum developer is the hero, and we are all just supporting actors. And supporting the quantum developer should be our North Star. And if we leave this conference with that common purpose, I believe we will leap into the quantum era.